Hello everyone, my name is Nurjana Bidin Maraziz and my metric number is 299020.
Hey, hi guys, my name is Masara Jomazmi and my metric number is 299361.
Hello guys, my name is Anushree Ravindran and my metric number is 301846. So guys, today we are going to learn how to solve a linear programming graphically. Imagine a company that produce two products which is X and Y, which is they want to maximize their profit.
Okay, alright, I know. Let's start by defining our objective and constraints.
Okay, so equals to 3x plus 4y. This is our example only.
Got it? What are the constraints?
So in the graph, we actually got three constraints. For the first constraint is x plus 2y lesser than 8. And for the constraint 2, x plus y lesser than 5. And non-negativity constraint, which is x bigger than 0 and y bigger than 0. So now that we have the objective and constraint, let's plot them on the graph. So to plot each constraint, we will first turn the inequalities to the equalities to get the line. For x plus 2y equals to 8, if x is 0, then y is 4. Then if y is 0, then x is 8.
Exactly. Now for x plus 5 is equals to 5. If x equals to 0, then y equals to 5. And if y equals to 0, then x equals to 5, right?
And now that we have point for both lines, we can draw them. The feasible region will be in the first quadrant where both constraints overlap, representing all solutions that meet the constraint.
So now we find where these lines intersect to identify the corner points. Right.
Right. The corner points are 0 and 0 where the axes meet. For the number 2, 5 and 0 where the x plus y equals to 5 meet the x-axis. For number 3, 0 and y is 4 where x plus 2y equals to 8 meet the y-axis. And for the plot number 4, which is 2 is x and y is 3 where the two lines are intersect. So now that we have the corner points, let's evaluate the profit of each point. First, we substitute each point into p equals to 3x plus 4y, where where the first plot is 0 and 0, so the p will be 0. And for the second plot is 5 and 0, which is p will be 15. And for the third plot, which is 0 and 4, the p will be 16. And for the fourth plot, which is 2 and 3, p equals to 18.
Also, the maximum profit for 18 occur at 2, 3.
That's correct. To maximize profit, they should produce 2 units of x and 3 units of y.
Exactly. That's how you solve an linear problem graphically. The company's optimal solution is 2 units of x and 3 units of y for a maximum profit of 18. All of you understand?
Yeah, I understand. Thank you, Anu. Can we move to next question?
Okay. All right. Let's dive into an interesting case in linear programming for the question 2. So what we actually going to explore what will happen when the objective function is parallel to one of the constraint.
Parallel lines in LP. I didn't thought about that, and how does it affect the solution?
Great question. Let's go through a specific example to see what happens. Here, the objective is to maximize z equals to 3x plus 2y, and we have these constraints. First constraint is x plus 2y less than 10. Second constraint is 3x plus 2y lesser than 18 and 3x are more than or equals to 0 and fourth y more than 0.
So what are the unique about this constraint?
If we rearrange constraints 1 and 2 to solve for y in terms of x, we get 4, 4x plus 2y lesser than 10. We have negative 1 over 2x plus 5. For 3x plus 2y lesser than 18, we get y lesser than half x plus 9. Right.
Oh, I see now. Both constraints have the same slope, so they are parallel.
Exactly. When the lines are parallel, they don't intersect. It creates a unique situation for our visible region and for the objective function.
Interesting. So how does this affect the solution?
Well, let's add one more layer. If we rewrite objective function z equals to 3x plus 2y as negative 3 over 2x plus z over 2, we see that it has the same slope as the constraints. This means the objective function line can also be parallel to the constraints lines when we vary z by shift this line up or down.
Yes, if the objective function is parallel to one of the boundary constraint to the other boundary is a part of visible region where we could have multiple optimal solution along this boundary line. The objective function can slide along the constraint line so every point in that line within the visible region has the same optimal value for x.
So in other words, if the objective line and constraint line are aligned along part of the boundary, we'll get the same maximum value at multiple point on that line.
Yes, it's called solution multiplicity in linear program. But there is another scenario. If the parallel constraint line lies outside of the visible region, then the objective function cannot touch it within the visible region, meaning it won't contribute to the optimal solution at all. So the parallel lines can either give us whole range of optimal solution or no feasible solution at all, depend on whether they intersect the visible region or not.
That makes sense. So parallel constraint can either expand or eliminate our optimal solution based on alignment with the feasible region.
Precisely, this scenario shows us the importance of the slope alignment between constraint and the objective function in determining whether our solution is unique or has multiple options.
Exactly. Thanks, everyone. That's a unique twist in linear problems, programming problems, showing that the slope of line can change the outcome of an optimization problem.
Okay, let's start into question 3.
Yes, let's talk about the limitation of the graphical method in solving linear programming problems. That's actually we can see in the question number 3. It is visually helpful, but there are some challenges.
Okay, right. I heard is mainly used for simple problem with two decision variable. What is that?
Exactly, but the graphical method works best for linear programming problems with two variables, since we can easily plot them on the three-dimensional graph. But as soon as you add the third variable things will get complicated because you need 3D graph, and anything with four or more variables, it is impossible to plot visually.
So, for problems with higher dimension or many constraints, graphically solutions just aren't practical.
That makes sense. And what's about constraint? How does the number of constraint affect things?
Good question, my Sarah. With each new constraint, you will be adding another line to the graph. For example, in the graph that we show in the Padlet, we have this constraint which is 2x plus 3y lesser than 20. it will be the blue line. And for the constraint number 2 is x plus 2y lesser than 15. It is the orange line. And the third line is 0.5x plus y lesser than 9. That will represent the green line. The shaded gray area where all the constraint is overlapped in the visible region, which is representing the possible solution that meet all the constraints.
So each line we add make the graph more curated and harder to interpret.
Exactly. As the lines multiply, the visible region becomes a complex shape, which make it challenging to identify, shade, and accurately locate the intersection points. Plus, finding exact coordinate at this intersection can get tedious if high precision is required.
And that's another key point. The graphical method is not the ideal for accuracy. It is more of a visual tool, and for the larger problems, it become inefficient and cumbersome.
So in real life application like optimizing a supply chain, this method wouldn't work.
Yes, correct. For the larger scale problems, like those with multiple variables and constraint method, like the simplest algorithm are preferred because they are built to handle the high dimensional problems more eventually ineffectively can calculate the exact solution for a problem. So the graphical method is limited by both dimensionality and complexity of constraint, making it ideal for simpler and lower dimensional problems. But for more complex application, we need advanced algorithm.
Oh, I got it. Graphical solutions are helpful for small example but can handle large real-world LP problems. Then for explanation. Okay, now let's discuss about the benefit of graphical method.
Okay, so now my turn to explain. Firstly, the first benefit is a visual representation. By using the graphical method, it will provide a clear visualization of the visible region, its constraint, objective function line, and this will help users intuitively understand the problem and identify the visible solution. Second, it is simple to understand, where for small-scale problems with two variables, graphical methods are straightforward, making them easy without extensive mathematical knowledge. And it is also easy to identify the optimal solution. By plotting the objective function line on the graph, it is easier to see where the optimal solution lies, which is at the intersection of constraints, facilitating the process of finding maximum or minimum values.
Other than that, I would to add one more, which is highlighting constraint and boundaries. Graphical method make it easy to see how constraint interact and limit the solution space, helping to understand which constraints are binding and which are not.
Okay, for the question 5, let's discuss how to plot the constraint and the objective function in the graph.
The graph is in the graphical solution method for linear programming, constraints and the objective function are both plot on a coordinate plane to identify visible solution and find the optimal one. First one, how to plot the constraints. First step is we must rewrite the inequality as an equation. For instance, 2x plus y lesser than 100, 2x plus y equals to 100. Second step is one point can be found by letting x equals to 0 and solving for y. For example, 2 multiply 0 plus y equals to 100, and the point we will get is x equals to 0 and y equals to 100. Thus, the second point can also be found by letting y equals to 0, and it will be 2x plus 0 equals to 100, and 2x equals to 100, and x will get 50, and the point we'll get is x 50 and y 0. And we have to shade the region on the graph that satisfy the inequality, as this represent the visible area that meets the constraints.
Then how to plot the objective function line?
To be able to plot the objective function line, we need to insert a figure to represent the objective function into the formula and solve it in the same way as the constraint. And first, we have to let the z equals to 6. This will be 60,000 equals to 30 multiplied by 0, and plus 40y, and it will be y equals to 1,500, and the point will get 0, x 0, and y 1,500. And then we'll do the same, which is y equals to 0, and the point we will get is x equals to 2,000 and y is 0. Then the second step is plot the point in the graph and draw a straight line through these 2 points. The objective function line can be shifted parallel to itself by adjacent z to see how it interacts with the visible region defined by the constraints. This step will help to find the optimal value.
So if maximizing Z shift the line outward until it reach the last point in the visible region. If let's say we minimizing the Z, shift the inward or toward the origin until it touch the visible region. Is that correct?
Yes, this is correct. Next, to identify the optimal solution. The optimal solution Z is usually found at a vertex of the visible region where the objective function linear line is either maximized or minimized within that region. This is the point where Z achieves its highest or lowest value depending on the goal.
So Jana, we want to know what constitute the feasible solution area on the graph of LP model.
Based on my understanding, the visible solution area is the area where all the constraints of the linear programming problems are satisfied simultaneously. In the other words, it is the collection of all visible solutions of the linear programming, and it is possible for linear programming visible region to be empty, resulting in invisible linear programming, which has no optimal solution. Are you guys understand?
Yes.
Very clear.
Thank you, Jana, for explanation. Alright, we continue with a linear program problem and find the optimal solution using a graph. I will show you how to draw the feasible region and evaluate the objective function.
So where do we start? I'm so
So-
excited to see how this works. So where usually we start?
Okay, we start with a constraint. I plot each constraint as a line on a graph to show the feasible region. Let's look at our constraint one by one. So here we have x plus 1 less than 4. The second one is x less than 3. And third one, y less than 2. And the last one is x and y more than 0. Each of these define an area on the graph.
Why do we plot these lines? And what do they present?
Oh, good question. Each line represent a limit on x and y, dividing the graph into regions. We are looking for a feasible region, which is where all these constraints overlap. This is the only area where we can get a solution that satisfies all the constraints.
So how do we find this feasible region?
We shade the area that each inequality cover. For example, x plus y less than 4 will be the region below and including the line where x plus y equal 4. The other constraint will limit is further. Once we shade all the region, the feasible area will be the part where all the shade regions overlap.
So the visible region is like a polygon, right?
Yeah, exactly. This polygon has vertical and corner points. The key is that our solution, the point that maximize and minimize our objective function, will always be at one of these verticals.
So how do we know which vertex give us the best answer?
This is where we use the objective function. We'll substitute each vertex into our objective function, z equal 3x plus 2y, and calculate the value. The highest value will be our optimal solution.
Could you show us the calculation?
Absolutely. After plotting, we find the feasible regions. Verticals are at this point 0, 0, 3, 0, and 2, 2. Now let's calculate z at each point. Okay, at 0, x 0, y 0, z equal 3 multiply 0 plus 2 multiply 0 equals 0. And the second one is at x 3 and y 0, z equal 3 multiply 3 plus 3 multiply 0 equal 9. And the fourth one at x3 and y1, 0 equal 3 multiply 3 and 2 multiply 1 equal 11. And the last one is at xy and y2, z equal 3 multiply 2 plus 2 multiply 2 equals 10. The value of z is 11 at the point x3 and y1. So this is our optimal solution.
So we just check each corner point to find the maximum and minimum.
Yeah, this method is known as a corner point theorem and it guarantees that the optimal solution for LP problem will be at one of the vertical of the visible region.
This makes so much sense now. Thanks for your explanation, Mike. Can we move to the last question?
Alright. Wait for a while. Okay, for the last question, we're going to learn how to graphically solve an LP problem and we'll go through how to finding the solution difference between a maximization and minimization problem. Sounds good?
Yes, because I'm so curious about how the approach changed between the maximizing and minimizing.
Okay, great. Let's go through each steps using an example. Our problem has this constraint. The first one, x plus y less than 5. The second one is x less 3. X less than 3. The third one, y less than 4. And the last one, x more than 0 and y and more than 0. Okay, the objective function we are using are from maximization, minimize z equal 2x plus 3y. For minimization, z equal 2x plus 3y. We'll go through this by plot and constraint, identify the feasible region, determining and the corner point, and then evaluate the objective function at each corner point.
Sounds good. So, how do we start?
Okay, for the step 1 is to plot the constraint. Each these inequalities will form a line on the graph. For instance, x plus y equal 5x, x plus y equal 5 will be the line and inequality x plus y less than 5 represents the area below or on this line.
So we just draw each line and then shade the region that satisfy the inequality.
Yeah, let's do that for all constraints. Once we shade the region for each inequality, the overlapping area will be our feasible region. That's for step 2.
Got it. So, after finding this feasible region, what's next?
Okay, the next step is step 3, where we are determine the corner points and feasible region is a polygon, and each vertex or corner point represents a possible solution. In LP, the optimal solution will always lie at one of these corner points.
So why only the corner points?
Okay, I think that's a good question. This is because of the corner point theorem for a line objective function over a line feasible region. The maximum and minimum value will always be at one of the vertices.
Makes sense. So, what do we do with the corner points?
That's question for the step 4, which is we'll evaluate the objective function at each point corner. For maximization, we find the highest value of z for z equal 2x and 2x plus 3y by among the corner points. And for minimization, we'll find the lowest value.
Can you show us the calculation?
Of course, after plotting, the corner point of our feasible region are x0, y0 for the first one. For the second plot is x3, y0. And the the third one is x3 and y2. And the last one is x1 and y4. Now let's evaluate z equal 2x plus 3y at each of this point for both maximization and minimization. You can see all the constraints after we calculate. So for the maximization, the high value of z is 14. and at the point xy and y4. So that's our optimal solution for maximizing z. For minimizing, the lowest value of z is 0, which is at x0 and y0, making that our optimal solution for minimizing x.
So, for maximization, we found the solution with the highest Z value among the corners. And for minimization, we picked the lowest Z value. Is it right?
Yeah, exactly. Big true. It which is in maximization problem. We look for for the highest achievable value within the festival region. While in minimization problems, we go to the lowest value.
Thanks for breaking it down because I get how the approach changed based on whether we are maximizing or minimizing. Thank you.
Oh, I'm so glad that this helped. Once you understand how to apply this step, you will be ready to solve any LP problem, whether it's maximization or minimization.
Okay, thanks, Mai.
Okay, thank you guys. Thank you so much for taking the time to discuss this question.
And thank you too, guys.
Thank
You
you too.
guys,
Thank
all
you,
the
Anu and Jana.
expectation.
Thank you. Thank you. Bye.
Bye bye.
Bye.